Aí quando eu colocar aí, eu sempre desligo ele daí. Ah, tá, quando apareceu o off, né? Tá bom.
Gilberto está aqui? Gilberto está aqui, São Paulo?
Ele vai chegar quinta-feira.
Vai ver de longe, talvez.
Tá vindo, né?
Ok.
Pode começar?
Pode.
Agnaldo, dá para ligar o ar-condicionado? Tá ligado? Tá bom. Então, gente, bom, bem-vindos. Quem vai lecionar esse curso vai ser o Lucas. Tá? Aqui, basicamente, o que ele vai apresentar aqui, ele vai tentar fazer uma coisa autocontida, para os que não têm contato com mecânica e estatística. Só que daí, rapidamente, vai passar para as coisas que ele desenvolveu na tese dele e também em alguns resultados que foram desenvolvidos por um outro estudante que chama João Maia, que vai apresentar a tese agora no workshop que a gente vai ter em fevereiro. Tá? Meu nome é Rodrigo Bissacô, esse é o Lucas Affonso, né? E é assim, o curso ele está anunciado em português. Quem for querer créditos por essa disciplina pode entregar as listas em português, vocês podem, em português. Pode mandar uma material em português. A gente vai criar um Google Groups para discussão, para quem tiver dúvidas, tudo mais, para discutir a disciplina, os alunos que quiserem os créditos depois para esse curso. Aí vocês mandem um e-mail para o e-mail do Lucas, que está ali, tá? Que deu o Agnaldo. O Agnaldo, dá um close lá no e-mail do Lucas, lá, por favor, né? E aí, envie o e-mail que a gente vai criar um Google Groups, aí vocês podem discutir lá, pode ser em português ou em inglês, mas quem não tem inglês ainda suficiente para achar que vai prejudicar, vocês podem entregar todas as avaliações em português e tudo mais. Então, eu peço desculpas àqueles que não têm inglês fluente ainda, mas a universidade está oferecendo várias oportunidades para vocês aprenderem, então eu sugiro que vocês aproveitem essas oportunidades, tá? E a gente vai fazer em inglês justamente porque tem pessoas de outros países que estão interessadas nesse tópico, alunos, gente que tem outros lugares que escreveram para a gente. E aí, se a gente faz o curso em português, justamente a gente perde todo o resto das pessoas que a gente poderia interagir, e vocês também ficam mais uma vez atrás dessa coisa de conseguir fazer, escrever e entender coisas em inglês. Então, não tem problema de entregar as avaliações em português, só que o curso vai ser inteiro em inglês. Tá bom? Então, quem tiver dúvidas, quem tiver problemas com isso, me procura, que a gente pode conversar, mas efetivamente a disciplina vai ser em inglês. Tá bom? Então, pode começar aí, Lucas.
Beleza. So, okay, I need to say two more words about the conference. If you don't know the website of the conference, you can reach by looking through the web page of Rodrigo Bissacô. This the second web page is the web page that I created for this course. So I will try to put the exercises in this address, and also I will write some notes, and I will put there also. So okay, let us start. Okay. First, I want to say some words about statistical mechanics. Statistical mechanics is too broad a subject, because when I was preparing the notes, I was looking for references, and I mainly based my presentation of today on chapter 3 of Sasha Fröhlich and Ivan Velenik book. This chapter is called the Ising model, and is freely available online on Velenik's web page. You can search Ivan Velenik, you reach his page, and then you go to book, and you will find all this book freely available. So, as I was saying, although I will base my lectures on this material, at least in first moment, there are many books of statistical mechanics that are relevant if you want to look. There is Georg's book also. I don't remember how to write his full name, but you can look for Georg and Gibbs measure. It's also a good book, but it's usually a book for a second read. Okay, so what is statistical mechanics? What we are trying to do is try to model a system, the collective behavior of a system, by looking to some microscopic information of this system. And today I will try to give you a rigorous meaning, at least at first, of what this means. So, first, statistical mechanics, you can study it on the continuum, you can study particles that are quantum in nature, but in this course I will fix on particles that are that have a spatial distribution that is rigid. So they are fixed in a lattice, and I will say what I mean by this, that have some degrees of freedom that we will call spins. So particle with spin in a lattice. So what is the lattice? We start by fixing a positive integer, b, and the lattice will be an infinite graph where the vertex set is given by the b upples of integers. So they will be x1. I will write x equals x1, x2, xd. And the set of edges will be all the pairs of points here. I'll write like this, all the pairs of points such that their distance in the L1 norm is equal to 1. What I mean by L1 norm, I mean this. So you just sum from I equals to 1 to D of the absolute value of each one of the integers in this D tuple. So what it looks like? It looks like this. So of course, I'm not able to draw an infinitely extensive lattice here in this blackboard, but you can imagine this pattern repeating itself. So this is D2. And the degrees of freedom of each particle in a point, in some point here, will be allowed to vary in a discrete set. So the state space, that is the degrees of freedom, will be always discrete. Always discrete. For example, we can have at one side of ZD, you can have a spin that can only take two values, -1 + 1. This is the most important one for this course. This will be Ising spin systems. But you can also have something like 0, 1, or even 1 until a positive integer q larger than or equals to 2. So this is the most general one in the discrete case, the finite discrete case. But in statistical mechanics, you can study not only this kind of spaces, you can do with much more generality. If you are interested in this, you can look at Georgi. He does this in much more generality, where the state space can assume values in a polished space. So, for instance, it can be the real line, it could be the n-dimensional sphere, okay? But we will not talk about this. So, okay. What is the idea now? We want to study all the possible configurations. First, we will define all the possible configurations on the lattice. So, assume now that we are in this case. So, the spins can only take values plus and minus 1. So, the configuration space will be a collection of every possibility that you can see by choosing plus or minus 1 in each one of the points on the lattice. So, writing it down, it's just the product of the state space, the power ZD, and we write it something like this. This is a collection of plus or minus 1s. This is the configuration space on the whole lattice. But before we continue in this course, we will stay a little bit on this space as time goes by. But At first, I want to define now a collection of configuration space, not only on the whole system, but also in subsystems. So, you can also define local configuration space. In the following manner. First, you can fix a subset of ZD. At this point, it does not need to be finite at this point. And then you define the local configuration space as being the product plus 1 minus 1 to lambda. And this is similar to that one. Just a sequence of points that are plus or minus 1 inside lambda. So the first difference that we have from of this space to that one is that now I may have some space here that is not filled, in a sense that I don't know what happens to the configuration outside the set lambda. So we can define something that we call a boundary condition. That will be a configuration. The boundary condition is itself a configuration where we can use it to specify what happens to this configuration here outside the finite set, the set lambda. So it can be, we define it like this. So we can define this collection of sets that depends on the subset and on the boundary condition. This will be a subset of the space of all the configurations, and it consists of all configurations here such that if X is outside lambda, then the value of the spin at this site X is equal to omega X. We have two very important boundary conditions. You see, you have many boundary conditions, but we have two that are the most important ones. And these are the plus and the minus. And by this I mean omega X is equal to plus 1 for all X. And we have, I will write it like this. Okay? And also, similarly, we have the minus boundary condition that is defined like this. For these two special configurations that we'll encounter many times during this January, we have a special notation, and we denote the set of the configurations that have the boundary condition as this one plus, something like this, and the boundary condition minus, we write it like this, the plus and minus boundary conditions. Okay. I said to you that the idea of statistical mechanics is to study the microscopic phenomena by the detailed analysis of the microscopic picture of the system. So the idea is that you can describe all the possible configurations of your system as being something like this. But depending on the object that you are studying, you may have all the configurations right here are not equally probable. So we need to have a way to say what is the right probability to put on this space, so it can rightfully reflect the physical content of what we are trying to model. So the first thing that we will do now is to define an energy function. The energy function, also known as Hamiltonian function, is the one that will help us in the pursuit of the right way to describe states, the microscopic states of physical systems in this space. So the Hamiltonians that we will consider during this course are what we call the Ising type Hamiltonians. So this is a class of models. So now we will fix lambda to be finite, a finite subset, and I will not say anymore that this is a finite subset, but instead I will write a double inclusion, and by this I will mean lambda is a subset, and the number of points in lambda that I write like this is finite. Okay? So the Ising type Hamiltonians is a class of functions that depend on lambda and are defined like this. So these are functions from the local configuration space to the real line. They are given by this expression. Okay. So what this means? This first term here is the actual interacting term, because what you are doing is that you are taking the product of the two. If you have a configuration, so you have a collection of plus and minus ones, then what you do is that you take the product between two spins, the spins located at the sites x and y inside this box, and the intensity with which they interact is given by j, x, and y. And also we add a term that only depends on one site that we call one-body interaction, or the magnetic field, that is given by this expression. So you just multiply the spin by some number. So we have some restrictions at first on these numbers. First, they are all real numbers, of course, all real numbers. So the second thing is, okay, so at this point, this is completely general. They just need to be real numbers, and then you have a whole class of Ising Hamiltonians. But in order to better study them, we need to restrict our choices of coupling constants and magnetic fields. So I will give you some examples to illustrate this. The first example, I guess, is the most important one, is the most widely studied model, is the nearest neighbor Ising model. That is given by the following. You start the jxy, they will be given by a real number j if x minus y, their distance in the L1 norm, is equals to 1. So remembering the lattice structure, if this is x, you can only interact and 0 otherwise. So remember the lattice structure. X will only interact with its immediately nearest neighbors. Okay. Okay. So sorry. So x and y. You can consider J to be positive. In this case, the system is called ferromagnetic. And in the case that J is negative, this is called anti-ferromagnetic. You can consider Hx to be a constant, to be equals to some H for every X in ZD. And then you have, if this is different from 0, you have behavior, and if this is 0, you have another behavior. We will see this this week, maybe. So, okay. We say that the Ising model has short range, okay? Short range. If we have that j, x, and y equals to 0. If there exists a real number r, positive, such that every time that the distance between x and y is larger than r, this implies that j, x, y is 0. So, as you can see, the nearest neighbor Ising model is a prototypical example of a short-range model, because if their distance is larger than 1, then the interaction is 0. So, Otherwise, so if this is not satisfied, we call the model long range. And now another example. We can define j, x, and y to be given by j, x minus y to some power alpha if their distance is larger or equal to 1, and if they are equal, then you call it 0. So, as you can see, this model, in this case, it's obviously long range. So, okay. If you look to this expression of the Hamiltonian, you will see that we only see the local system. We are not seeing what's happening outside this finite set lambda. So there is a way to consider what is happening outside the box lambda. There is a way that your system can see what is happening. And this way is by adding a term to consider interaction with the outside. We need to add a term that will be called a boundary condition term. And we define the boundary condition Hamiltonian by this expression. You consider first this term right here, we call the empty boundary condition Hamiltonian. And then you add an interaction between the inside of the finite set with the outside of the set. And what happens outside, the boundary condition we are considering is omega, so the spin should be omega y. And this imposes another restriction to our choice, because as I said to you before, the set lambda we are considering here is finite. So the outside of the set, the complement of the set, is infinite. So in order to this term to be well defined, we must restrict the possible decays that we have here. And for that series to be well defined, we can consider alpha larger, strictly larger than D. Okay? Yeah, exactly. Thank you. Minus, exactly. So, okay, so alpha larger than D. But of course, these are in a larger class that we call the deterministic models, because, as I said to you, this class of models are completely general. For instance, the HX could be depending, could be spatially dependent, and this is a system that Rodrigo started studying here, and we will talk a little bit more about this one. But also we can go to another class of models where the JXY or the HX, both or only one of them, are random variables. So these are not deterministic anymore. These are random systems, and this is the kind of system that João studied in his PhD thesis. So we will talk a little bit more about these systems later. So, okay. Now we have the Hamiltonians. We have everything that we need to define the pressure. So, what kind of behavior we are interested, what kind of microscopic behavior we are interested in studying? So, in statistical mechanics, we are interested mainly in equilibrium statistical mechanics. We are mainly interested in the phenomena that we know as phase transition. So, a phase transition is a phenomena that happens when you look, not when you look only to the microscopic part of your system, but it appears only on the microscopic limit. So you cannot say that a piece of metal is magnetized by looking at each atom. So you need to see what's happening in the whole system. You cannot see that the water is frozen by looking to just one molecule of water. So you need to go to the microscopic limit and see what happens. So, and usually what is accepted is that a phase transition is related at first to some bad behavior, let's say, some bad behavior of some thermodynamic quantity. And what kind of thermodynamic quantity we are look today is something that we call the pressure. So first, let us start with a definition, the local pressure. I will introduce something that will be a little bit mysterious right now, but I can assure you that will make sense after, actually tomorrow it will make sense. And this is the something that I will introduce is the partition function. So the partition function is given by this sum. It depends on the box. So you fix a finite set of ZD. You fix beta, a real number that we understand it as being the inverse temperature of the system. Okay. And we define the partition function as being this sum right here. So it can depend on beta, on h. Right now we will consider h to be, actually it doesn't matter, but we will consider beta, h, you understand this h here as being a family of numbers, okay? And with a given boundary condition omega, and okay, and the partition function will be defined as the sum over all the configurations, of the exponential of minus beta h omega sigma. This is the partition function. This is a somewhat mysterious function right now, but it will make much more sense when we start talking about Gibbs measures, where this partition function appears as a normalizing factor to some probability measure. So, okay. Then the local pressure is defined as 1 over the size of lambda times the log of the partition function. And as you can see, since this depends on beta, h, and omega, the pressure will also depend from of beta, h, and omega. So you have at first a family of local pressures. Okay. The first thing that I want to draw your attention to is that I can take the log of the partition function, because in this case this will never be 0. Okay, this is an exponential of a real number, so this is not 0. So this log is well defined. And the other thing that I want to draw your attention to is that whatever the bad behavior that we are looking for may be, this is certainly not a good candidate for it, because if you can actually take derivatives of this function with respect to beta and h, and they will always exist to every order. So this is not exactly what we call bad behavior. So in order to a question? No, okay. So what we need to do is to find this behavior, this bad behavior, is we need to go to what we call a thermodynamic limit. So in search of the bad behavior, we can go to the thermodynamic limit. Dynamic limit. But why? When you look to real systems, you will see that when they are passing through a phase transition, there is some sort of discontinuity somehow that is happening. When you can see a sudden change in your system in some aspect. For instance, if you are heating water, liquid water, then when it starts to go to the gaseous phase, it will suddenly expand. So you see, we are trying to look for some wild behavior like this, some discontinuity with respect to something. So as I told you, this function it's very good. Actually, there is derivatives as many times as you want. So our only hope to search for some bad behavior like this is to go to the thermodynamic limit. So this is the first problem and the main theorem of today's class, to show that this limit in some sense exists. So first thing is that this sequence, the local pressures are actually indexed by finite sets. So what do I mean by taking limit in this case? So first, let us define what I mean by taking limits. Okay. Oh, I'm sorry. Equal. This is equal. Okay. Let me write again. So lambda, omega, and we have beta h equal. So it's equal. Okay? Okay, so taking limits in the lattice ZD. So we say just a minute. So what do I mean by taking limits here? So we will start with a sequence vectored by the natural numbers of finite subsets of ZD. Okay, that should satisfy three things. The first one is that they are one inside the other, the next one. So this holds for every n. Okay. The second is that they are this property we call increasing. So the sequence is increasing in the sense that the previous finite set is contained in the next one. We know that if we take the union of all lambda n, okay, this should be the whole lattice ZD, and this property we call invading. And also they need to satisfy a geometric property that we call Van Hove. And I need to make some drawings to explain to you what this means. So consider this sequence. Lambda n will be given by minus n to n to the power d. Okay? So what this looks like. So if we're looking to the ZD, Z2, this is 0. So you will start 1, 2, n. Same thing here, minus 1, minus 2, minus n. So a box lambda, this kind of set we'll call it box because it looks like a box. So you have this interval right here, you have this interval right here, and every pair inside this square will be inside this one. So for instance, this is 43, so this point right here, 143, is inside this box. Okay? And as you can see, if I grow this box, okay, if I go from n to n plus 1, then the next box will contain exactly the last one. So this box is lambda n, this one is lambda n plus 1. The next thing is that it's obvious that when you take the union of all the boxes, eventually you will reach the whole ZD. So it's invading. But there is also another important property, is that you can, if you look to the boundary of a box, and what I mean by boundary, the boundary of a box is the set of the points that are this is the set of points that are inside the box that are most closely that are close to the outside. So this point here is in the boundary. This one is not on the boundary. So the boundary of a set should be something like this. So, okay, this is the boundary. So, in the case of the box, it's not hard to convince yourself that the volume of this box, the quantity of the points that are inside of this box, is roughly n squared. And the boundary, you can see that have only roughly 4 times n points. So this behaves like 4 over n. And when we take the limit, when n goes to infinity, this goes to 0. So in order to take the limit in ZD, we will ask also that that property is satisfied. So the property of the limit. That property of the limit. So if first the boundary of the box is defined as the points inside lambda n, such that there exists a point outside the finite set, such that its distance is 1. So only the points that are inside the box and that are nearest neighbor to outside of the system. If we define something like this, we say that the sequence satisfies the Van Hove property if the limit of the boundary over the size, the volume, goes to 0, is equal to 0. So the first exercise that I want you to think about, I will write right here. First exercise, just to get used to this property right here. Actually, this is the most important one, as we will see shortly. So the first exercise is that find a sequence 1, find a sequence such that it satisfies 1 but not 2, the property 2, and also one that satisfies 1 and 2, but not 3. Okay, so any questions? Okay, so now we start defining what this means in the thermodynamic limit. So the theorem is for any sequence of finite subsets of ZD that converges in that sense, converging in the previous sense, we have that the limit is this quantity right here. It will exist and will always be some number that depends on beta and h. Okay? So, okay. For this limit to exist? Good question. I guess if you consider them bounded, they certainly, if hx is bounded, it certainly exists. But I can't recall right now. We will see during the proof, but I guess bounded works. But otherwise, I don't know. Okay? So the proof will be divided into some steps. The first step is that we only consider a finite range system. Okay? Remember, this means that there exists an arm positive such that Jxy equals 0, such that if the distance is larger than r, then Jxy is 0. The second thing that I didn't mention is that all the examples that I gave you, the part with the two-body part of the interaction satisfies the following property that we call translation invariance. This means that if I consider Jxy and I translate it by some other point z, this is the same as Jxy. So as you can see, since the L1 distance is invariant by translation, if you have 2 points that are nearest neighbors, if you translate the 2 points by z, then it's still, they will be nearest neighbors, and the interaction will be the same. And by the same reason, the long-range model, since it depends as the inverse of the distance to some power, it will be translation invariant. But if you don't believe me, check it for the previous examples. Yeah, they need to be translation invariant at some point. Okay, yeah. At least for my proof, they need to be translation invariant. need to be regular. Yeah, exactly. So the other condition, good point. Another condition is that we call regular. And what does this mean is that for any x in ZD, actually regular means something stronger, means something like this. Okay, it's translation invariant, so I can write like this. J 0x for every x in ZD minus 0 should be finite. But as you can see, in this case, the regular hypothesis is trivially satisfied because this is finite range in this case. This will be important only when we consider long-range systems. And basically, it's because of this condition that we have the restriction in the decay parameter alpha. Okay? So we need this. Okay, second step. Let us study first a very particular sequence of boxes. Okay. Yeah, exactly. Yeah. Okay, okay, yeah. Actually, the pressure functional, the pressure have a very rich history. Actually, it can be generalized for in a much more general context. For instance, you cannot restrict yourself to Ising type systems. You can consider interactions that can depend on many bodies, not just two or one. And you have a pressure defined for interactions like this. And actually, there is a very good book now that Rodrigo talked about this for a general treatment of the pressure. You can look to the book. You can look at this book right here, Convexity in the Theory of Let's Guesses. Let's see guesses by Robert Israel. So he managed to drive to put the pressure function in a much general context and prove very strong results on the nature of this transition in statistical mechanics. And if you want to learn a little bit more, you can look at his book. Right now, we will only consider Ising type systems. So, okay, going back to the existence of the limit of the pressure. So, okay. So, first define. So, define these sets Dn, and the Dn will be boxes also, but boxes of a somewhat different nature. So they will be 1 until 2 to the power n to the power d. So what they are? What are these boxes? They are or something like this. Again, you have Z2. And what is the n? The n is some set like this. 1, 2, 2 to the power n. So it's a box like this. An advantage of these boxes is that we can divide our lattice according to the translates of this box right here. So if I sum every point, if I write something like this, y for a given y in ZD, I can translate this box, translate by summing times 2n. Then you sum to every point inside the n, you sum 2 to the power n times y. Okay. X inside. So what this means, for instance, look at this box right here, the n. If I sum the point y equals, if I sum y equals to 1, 0, then the first point here will be 2n plus 1. Okay, so 2n plus 1 in the first coordinate. So the set will actually start here. And since the second coordinate is 0, you will do nothing to the y axis. So you have something like this. We start here 2n plus 1 and go up until 2n times 2. So 2n plus 1. dn y. Although we have a space between these two boxes, remember that we are only considering lattice points. So although this drawing has spaces, there is no space in the lattice between these two sets. Okay, so there is no point here. So what happens is that then I can break the lattice using these sets, these sequences of boxes that have a side length of 2n. So I will first show that the limit exists, the limit of the pressure exists for this sequence. Okay. Let us remember the Ising Hamiltonian. For this proof, we will consider the empty boundary condition Hamiltonian. At the end, I will discuss what happens when you consider a boundary condition Hamiltonian instead. So, okay. So, first, remember the Ising Hamiltonian. So, it was this jxy sigma x sigma y xy inside dn plus 1 minus hx, oh sorry, x inside here, hx. dn plus 1. So, okay. Consider now n equals to 2. So you have 8 points here, 8 points here, and this is your box. This is D3, okay? Notice that the D2, in the way that we define it, will be this box right here. 1, 2, 3, 4, 1, 2, 3, 4. So this box right here, D2. So it is contained here. But look, we can, by translating the previous box, we can fill the rest of the larger box with smaller ones. So if I sum here exactly in this way, if I sum in this way exactly y1 and 0, then I will have this box right here. And if I sum here, I will have 0, 0, 1, and here I have 1, 1. Okay? So I can exactly cover the previous box, the larger box, with the boxes in the previous step. So, okay. But how this translates in respect to the Hamiltonians? So, can I write the Hamiltonian of the system as being just the Hamiltonian of each one of those parts? Life would be easier if I could do this, but I actually can't exactly. So, can almost do this. So, since dn plus 1 is a disjoint union of dny for some I, for some collection of i's. Actually, we know exactly what this is. So y should be, or we are doing in ZD, so it should be something like 0, 1 to the power of d. So this will take all the possibilities that we have here. Okay, so if you take d equals to 2, you get all your possibilities here. This is the same as doing nothing, the zero translation. So since we have something like this, we can try to divide the Hamiltonian using this decomposition. The part with the magnetic field is actually easy, because since this is a disjoint union, we can write the sum dn plus 1 hx sigma x as being just the sum over y in x in the, y in 0, 1 to the power d, and the sum of x in d and y of hx sigma x. So this was it. Now the other part, the actual interacting part. So what happens? Consider first an easier case where you have two finite sets. Okay, two finite sets that are disjoint in ZD. What happens to a term like this in this situation? So you would have jxy sigma I sigma x sigma y inside the union. What happens in this situation? Well, you have, since you are looking to pairs inside this set, the possibilities are, you can have the 2 points inside lambda. You can have the 2 points inside lambda prime, but you need to consider the interaction between the boxes. So you need to consider x in lambda, y, lambda prime, j, x, y, sigma x, sigma y. So this mixed term right here, first, we can see that this is the same as the Ising Hamiltonian with empty boundary conditions in the system given by the union of lambda and lambda prime. This is the Ising Hamiltonian with empty boundary conditions. In lambda, this is the one in lambda prime, and this one here I will call W lambda prime, because this is a mixed term, and therefore I will write it in a different manner. So every time I have a disjoint decomposition of the set, I can use decomposition like this. So I will use it to decompose this Hamiltonian using that property that I just told you. Okay, so Dn plus, so x and y, I feel I can write it directly. So what do you have? So since Dn plus 1 is a disjoint union of not just one but many different parts, what I need to consider here is for the second term here. The second term here that we'll call a star is the following. So star is the sum over all pairs first the sum over 0, 1 to the power d, and then the sum of the Hamiltonian with empty boundary condition. Why? Because, as I told you, you have the Hamiltonian in the smaller box, and since the magnetic field decomposes in this way, you can sum both, and then you get this first decomposition right here. But we have to consider the mixed terms. So the mixed terms are something like this. We consider y prime inside 0, 1 to the power d, and then I will write this as y prime instead of d and y prime. So just to make things easier. And of course, everything depends on the configuration. So, okay. The system doesn't exactly split as the spatial structure suggests, but it gives me something something close to this. We need only to consider the interaction between the splitting. So a first lemma is that I will control what's happening with this term. I will give a bound to this interaction here. Lemma. So there exists a constant C positive such that this term y prime is less than this constant. And I will explicitly write this constant for you. So let's start proving. So the first, we can use the inequality to pass the absolute value inside of the sum. So we have that this term right here is less than the sum of the absolute value right here. And now we just need to consider what's happening with these terms. So sorry. Yeah, for the C depends on n. Okay, so I just put C because I don't actually recall now the exactly dependence, but the constant is explicit, and so you see that C depends on n, depends on the dimension. Okay, so y. So what is this? So this is this string right here. So it will be less than the sum of x inside d and y, and x prime inside d and y prime. And since I pass the absolute value inside the sum, it will be jxy. Okay. Also, since the spins are just plus and minus 1, the absolute value kills the dependence on the spins. So this bound is actually uniform on the spin configuration. Okay. What is the next important part? Since this jxy is translation invariant and also is finite range, there is only a finite number of pairs that I need to check. Okay, so since jxy is finite range and translation invariant, the supremum over all pairs ZD of jxy, and this I will call j star. This is finite, of course. As I told you, this is true because you have translation invariance, so you just need to check a finite number of pairs, and okay, because it's translation invariant and short range. Okay, so but notice that this also holds for the long range model that we defined it before. So okay, so this implies that this sum on the right hand side here is less than j star times the number of pairs x and x prime inside ENY times ENY prime. Okay? Why translation invariance is necessary right here? It could be short ranged, but as you go large, as you go farther from 0, you could be like growing as a function of z, for instance. Okay? So this is why you need translation invariance. So okay, now we need to estimate how many points you have, how many pairs you have right here. So let's again take a look at the picture. What is happening? You are looking at pairs, not only all pairs. It cannot be all pairs because JXY is only different from 0 if the distance is less than R. So you are looking for all the pairs such that the distance must be at most R. This R exists because, again, the interaction is short range. So, okay. Let us look to this drawing right here. The worst case is the case where they are sharing a face, let's say. They are close. So what happens is that if I consider a point here at the boundary, this boundary here, that you can see as a face. If you consider this as a three-dimensional cube, it will be a face. In the case of Z2, it's just the side of the square. Then I will have all, in this set right here, I will have all the points that are in the other one, in this side right here, such that their distance is less than R. So this one is in the set, this one is in the set, this one is in the set, until I reach some point R, some point x prime, such that the distance is exactly R. Okay? So what happens is that, okay, so what this means is that every point that is in this set right here, that's my right. This means that every point inside x prime, okay, inside the set right here, x prime and dn y times dn y prime, okay, such that x y is less than R. Every point that is inside here, such that x is in a face of dn y. So a face is something like this, okay? So with this point right here, every point that is here, that is inside here. So, oh, sorry. Let me just take a look. Okay. Yeah, actually this bound will not work. I need to change something a little bit. This bound will not work because I will not count all the possibilities. So what we'll do is that I have the set and I will put this, the strategy is, I will put this set inside a larger one that is easier to count, and then I will count all these possibilities. So what happens is that every point that is inside this set have to be at most r from a point in the face. So every pair xy, so inside the set dn y prime, such that x minus x prime less than r, we know that it must be at most the distance, let's say it must satisfy that x, the distance from x to a face of some of these cubes should be less than r. Okay? Of course. But okay, so if this happens, the other thing that I want you to say is that certainly if I take some pair of points inside here, and I take a ball in the L1 norm, meaning that I will take all the points that are at most r from a given point x. Oh, let me just write it this. Draw this better. So you have something like this. So if I have x, a point here in the n, and I draw a ball in the L1 norm. Remember that in the L1 norm, the balls are diamond-shaped. So if you consider a ball of radius r, okay, this will certainly contain every point that is in dn y prime, such that the distance is at most r, obviously. So what happens is that this set, so this implies that the set of all points, all pair of points in dn y times dn y prime with the distance right here, they must be contained in the union of every point x, okay, every point x, such that the distance to the face is less than r, okay, and you take the union of all the balls, so the balls are the sets of x prime, such that x minus x prime is less than r, okay? Since this is an inclusion, do everyone understand this step? Okay, so since this is an inclusion, when I'm counting the number of points in this set, I just need to count this number of points to give an upper bound. So the number of points such that x minus x prime less than r. This will be less than this is a ball, but the number of points here doesn't depend on x, okay? Doesn't depend on x, so this will be just the number. Let me call b br0. This is the ball, the points that have distance at most r, times the number of points that have a distance at most r to the face. The number of points x inside the NY such that the distance to the face is at most r. Again, look at the drawing. You can map the points right here. Each one of those points, if the point x is a point right here, you can map it to some point in the face, okay? But there are at most r points in this line, okay? So until you reach the face. So this number right here will be at most the number of points in the face times r. Okay? But now it's not hard to convince yourself that since this cube have that when you have a box like this, a cube, a box like this, the number of points in the face are since you are fixing the last coordinate, you can have only two to the power n, because this is the side, this is the possibilities that I'm allowing, to the power d minus 1, and this, why this is d minus 1, because the face you fix it, in the face you fix it the last coordinate, so so you can only vary the other ones. This is why you get d minus 1 times r. Now you go back to here. With that inequality and this inequality right here, you get that this sum is less than the number of pairs that are different in 0, 1 to the power d, and this is easy to count. This is just 2 to the power d to d minus 1 over 2. Okay, because you are counting with multiplicity, so this is 2 d minus 1 times what? Times j star. What else? br0 r 2n d minus 1 r br0 2 to the n d minus 1. So as Henrique asked, what is this constant? The constant, you can take it to be j star r br0 times 2 n plus 2 d minus 1, or d minus 1. Why this n plus 2 is just to not have this term right here. You just bounded this term. Yeah, okay. You just make the calculations. You see that this coefficient works. This coefficient right here works. Okay. So since this is true, this means that the Hamiltonian in a larger box, okay? The Hamiltonian in a larger box. It can, you can, since this is not bounded in the absolute value, you can bound it. You can give an upper and lower bound, because this is using this constant. So this will be larger than the sum of y inside 0, 1 to the power d h d n y okay, minus the constant j star dr0 r 2 to the n minus plus 2 d minus 1. Okay, this is less than h d n plus 1 sigma, and a similar thing to the other side. But now with a different sign. Q 2 to the power n plus 2 d minus 1. Okay? So what this means is that, remember, the partition function is just a sum over all configurations, over all local configurations of the exponential of Pn plus 1 sigma, okay? And if I use this inequality, here we have a minus sign, we use the lower bound, we have the sum over all configurations. And here we have a product, 0, 1 to d to dy and sigma. Times a constant, exponential of beta. I will call this c, and we have 2c n plus 2 d minus 1. And a similar thing to the other side, using the upper bound. This will be the same, the sum, n plus 1, d minus dn, the product, y sigma. Oh no, sorry, the product is inside. D, and now a sum over all configurations, dn plus 1, and again exponential of the constant, the same constant. So what happens here is that I want to change the product with the sum, okay? But this is a finite sum, okay? So I'll just split this sum over the configurations inside only each one of the smaller boxes. So this is actually equal to the product of 0, 1 to the power d of the sum on the configurations inside dn y exponential minus d d and y sigma here. And now you can recognize this as being the partition function. This is the partition function on the smaller system. And remember, the system is translation invariant. So you can translate the system instead of y. You can translate the system to y equals to 0. So you can go all the way to the smaller cube. Sorry. Yeah, they need to be equal, exactly. So in this case right here, you need the magnetic field to be equal. Okay, so the magnetic field needs to be translation invariant also. Okay, thank you. Otherwise, you would not be able to make this. Okay, so. Yeah. Yeah, the spoiler is that the pressure doesn't see changes that are smaller than the volume. So if you consider at the end, we will see that if we consider a spatially dependent magnetic field, the pressure will not, the pressure will have the same limit as if the magnetic field would be constant, like equal to 0. Okay, so since these are all equal, and again, we know that this has 2 to the power d points, then I know that this product right here is just the partition function on the smaller box to the power 2 to the power d. So taking the logarithm, taking the logarithm of all these qualities right here, of all these inequalities right here, we have log of the partition function in the larger system is larger than the log of the partition function in the smaller system times 2 to the power d, okay? But we have a multiplication by a constant, so what is this constant? Plus the constant c times 2n plus 2 d minus 1. And the same thing on the other side. Okay, sorry, this is a minus, this dn minus 2d plus c times 2 n plus 2 d minus 1. So now you need to divide by the size of the larger box. You divide this by the size of the larger box. Okay? And this you also divide by the size of the larger box. But again, we know exactly how many points we have here. We need also to divide here. We know exactly how many points we have in this box. We have exactly 2 to the power n plus 1 times d. Okay? So in this term right here, since I have a 2d, and here I will have 2n plus 1 times d, this will be equal to 2 times n times d, and this is exactly the size of the box of size n, 2 to the power n, of side length 2 to the power n. And also here, okay, so what we have is that if we subtract from all the sides exactly this term right here, we can conclude that the log of ZD n minus 1. 1 over dn plus 1 minus log of z dn 1 over dn, the absolute value, because I have the same number both sides, okay, is less than a constant c that depends on the range, on the dimension, but doesn't depend on n, times 2n plus 2 d minus 1 over 2 n plus 1 over d, and this will be, we can write it as 2 times d, minus 1 over 2 n plus 1. And again, this is the definition of the local pressure in the n plus 1, and this is the definition of the local pressure in n, and we have a bound that is dependent. There is very small depending on n. So what you need to do is to show that the sequence, the sequence given by these boxes is actually a Cauchy sequence. So we need to consider this implies that for every m larger than n, if you do a telescopic sum and using this inequality right here, you manage to show, you can show that this is actually less than a constant times 1 over 2n minus 1 over 2n. If you do the calculation, you show something like this. So this shows that this sequence is a Cauchy sequence, so this will converge. So, okay, this is the first step. Okay, and I am, my time is over. What is next? So, what I prepared for today, and I couldn't do everything, is show actually the existence of the pressure, and also to show what happens when you consider boundary conditions and the decaying field. I will do this tomorrow, but why I'm doing this? The pressure is the first thing actually the pressure is the first object that appeared in the physics literature. So you will study this to prove phase transition. And why I'm showing you, why I'm bothering you with these things? Because I will show that for some systems that we study here in this group, that depends on the decaying field, the pressure cannot actually see the fine structure of the phases of the system. So what I will show you tomorrow is that when you consider, for instance, a decaying field, the pressure will have a limit that cannot see the influence of the decaying field. So what this indicates is that you need to study this kind of system. You need to have another notion of phase transition that doesn't depend on the pressure. And this is the motivation that we had to start studying. Actually, I had, because Rodrigo was already studying this a long time, to study what happens to the phases of the system with respect to a very special kind of probability measures that we call Gibbs measures. I will talk a little bit more about this tomorrow. So, thank you everyone. See you tomorrow. Any questions? Yeah. Yeah, exactly. Yeah, exactly. I will start with this tomorrow because this I only showed you that for one type of sequence you have convergence of the pressure. Tomorrow I will show that any sequence you have convergence, and this will imply that that when you put boundary conditions, it will not matter also, and when you put the decaying field, it will also not matter. Actually, if you have any sort of perturbation of your system in your Hamiltonian, that the contribution is not of the size of the volume, it will not matter to the pressure. So the pressure, in this sense, can only see what happens in the bulk of the system. It can't see more fine details. For instance, something dependent on the boundary. Yeah, exactly. finish, yeah. Corta. Cortar. Inclusive, isso é uma questão interessante, que, por exemplo, é uma questão até provar a existência de equilíbrio para coisas que são aleatórias.